Well, thank you also for the introduction. As you said correctly, I'm affiliated with the LMU in Munich and also with the University of Vienna, where I am doing my PhD at both, and I work together with Stefan Schweter, which is affiliated with the Bavarian State Library. And we developed the Cisteria system, which we participated in the HIPE 2020. And I will shortly present our outcome for that year's shared task. So I will super shortly explain the task and afterwards show our used data and resources with respect to the embeddings and also the language models we used, then shortly presenting our method and result in the end. So the task we picked, because there were several bundles to choose, was the coarse-grained named entity recognition for historical German. And here we have 5 different named entity tags, which you of course know is person, location, organization, time or date, and product. And we have to evaluate that in the literal and in the metonymic sense. So for those in the audience that may not be too familiar with that topic, here is a super short example for metonymy. So you have the sentence negotiations on the Concordat with Hanover are progressing. And depending on the context, Hanover can be considered as a location or as an organization. Okay. The data, so the HIPE data as such, I won't show too much because Maud already did it in the morning. From this HIPE data corpus, we took the German part, which is composed of Swiss and Luxembourgish newspapers from the last 200 years and was annotated by native speakers according to those guidelines Maud explained as well. So what do we find here? Different OCR quality, but also a broad spectrum of text. Here is a very short example to show what peculiarities we find there. So you have different kind of OCR errors. The one in the first line is not too bad. The end is only confused with a U, or the other way around. And we also have word hyphenization, where we have this special hyphenization symbol included in the HIPE data. In our pre-processing, we remove the hyphenization, and we also did some very simple rule-based sentence tokenization or sentence splitting. And in a reverse process, we came back to the original format for the evaluation then. So what kind of embeddings did we use? We used fast text embeddings, byte pair encoding-based embeddings, and FLAIR embeddings. And as a language model, not surprising, we did use BERT. What we did here was that we fine-tuned BERT in the first place with a Hugging Face library on the HIPE data. And then we extracted transformer-based word embeddings from BERT via the FLAIR library and used this feature-based approach. What does that mean? So we take for every token the first subword and compute the mean over all BERT layers to get a representation for that token. This is an overview of the different data resources we have. So in the first third, you see the fast text and byte pair encoding embeddings, which has different time periods and domains, which also holds for the FLAIR embeddings and for the BERT embeddings. So we have corpora from different time periods and also from different domains. And in the second table, we also tried to picture the size of the different training data for the embeddings. And the token size here is given in millions. So there is a very big difference between the different embeddings. And we will see later on in the results whether this has influence or not. And for the embeddings, we use already pre-trained resources. For fasttext, we use the embeddings trained by Mikolov, which are available, and for byte pair encoding, the ones from Senrich. And for the FLAIR embeddings, we have the ones provided by the organizers of HIPE. And we also trained own FLAIR embeddings on 3 different German corpora, which is the Hamburger Anzeiger, the Wiener Zeitung, and the Wiedergabekorpus. And for the BERT models, we have trained a model on the Europeana data, which stems from the Europeana newspaper corpora. And we have a very large German BERT model for which I cannot give any more detail by now because it is not released now. So what was our core idea? We just wanted to ensemble those different embeddings and language models to figure out how they work together somehow. So they are simply concatenated, and as I explained before, from BERT, there are also embeddings retrieved. And we also did train different embeddings for literal and metonymic sense, since we found that having a model for both did not work optimally. In the first step, we evaluated the best embedding per category, and in the second step, we stacked then the best embeddings. So this is a very simple graph of our method. So we have the different embeddings concatenated with a fine-tuned BERT, which we feed then in a bidirectional LSTM with a CRF layer on top, and then get the final annotated output. So what are the results for only the fast text embeddings? We find that the fast text embeddings trained on Wikipedia perform best, which is somehow surprising because the fast text embeddings trained on Common Crawl in the second line have much more training data as a background. So here the amount of data is not the point. And not surprising as well, the byte pair encoding underperforms here compared to fast text. If we look at the FLAIR embeddings, we find that the provided embeddings by the organizers perform best, which were trained on the HIPE data, with 2 percentage points difference to the German Wiener Zeitung. So here the winner is CLEF. And for the BERT model, also not very surprising, the biggest, or the model with the largest amount of training data, the large German BERT, is the winner. And of course, in German, the cased versus uncased BERT makes a difference, since German proper nouns are case sensitive, always written with an upper letter in the first place. So the cased models work better, of course. So then we stacked all of them and look what happened. And we find that the combination of fast text trained on Wikipedia and this very large German BERT model performs best. The adding of the pre-trained HIPE embeddings does not harm performance very much, but slightly. So we excluded that in our final setup. So our final Cisteria model looks like that, only using fast text and BERT embeddings. And we arrive here in the comparison to the other participating teams. On the left side, you see the literal sense, and on the right side, the metonymic sense. And for metonymic sense, we can achieve a good performance on the second or third place. And for the literal sense, we arrive at the fourth place on average. And what we also found, that our precision was very good, but our recall was somehow very bad. So we really would have to work on that. And compared to the best system, when reading their paper, we found that they used very different multilingual embeddings. So not only for one language, but for all. So that could probably help for our system in the future as well. So a super quick wrap up, what we did do. We wanted to evaluate coarse-grained named entity recognition for historical German. And we ensembled fast text embeddings trained on Wikipedia and BERT embeddings trained on large historical and contemporary data with a neural approach. So that's it from my side.